Want to start off today by talking about another kind of application of integrals that's easiest to imagine in the context of a tank that has water going in and water going out. So you've got, say, a faucet up here. Can I draw a faucet? Not very well. There's a faucet up there. Water's going in, and then you've got a drain down here. Water's going out. And of course, with the faucet, you could turn it on. You could keep it at a constant rate, so the water's flowing at a constant rate. Or you could play around with it and make it go faster or slower, maybe even in a periodic way, like a trig function or something. And then the drain, you could have either open or closed, or maybe you could have it partially open, and maybe you're kind of playing around with that and opening and closing it. So that could be a trig function too. It's a certain inflow here and a certain outflow here. Now, when I call something a flow, it's implied that that's actually a rate of change, a derivative, though I'm not going to use derivative notation. I could call the inflow, say, f of t, and the outflow, say, g of t, where t is time. The units for the flows would be units of volume per unit time, like gallons per hour, or I'll use liters per minute. Seems reasonable. Could do milliliters per second, but let's keep it at liters per minute as the units that we end up using for this flow rate, just for the sake of imagination. I'm going to go ahead and pretend these are not constants. And in fact, I'm going to use specific functions for these things. Let's go ahead and make them be trig functions. You do, technically speaking, want these functions for the flow rates, inflow and outflow, to be positive. I'm using 3 cosine of 2t here. Technically, that's not always positive. It goes negative. So in reality, I should either add something to this, like 4 or 5 or something over here, or I should restrict my domain to where this is positive. Let's go ahead and restrict the domain, say t going between 0 and cosine is first 0 when its input is pi over 2. That would correspond to 2t equaling pi over 2, so t being pi over 4. And if I use, say, a sine function for this one, I'm going to use 4 sine 3t. That's going to start out at 0, but then become positive. It'll go back to 0 when the input is pi. 3t is pi, so t is between 0 and pi over 3. Both of these are then going to be positive at the smaller value. Pi over 4 is smaller than pi over 3. So I'm imagining this to be a model of the flows for t between 0 and pi over 4, the smaller of these ultimately. To figure out whether the volume of water in liters is increasing or decreasing, I hope it makes sense. You'd want to think about what you could call the net flow rate, or the net flow for short, as the inflow minus the outflow. That's something that definitely could be negative, even when both of these things are positive. It's going to be the inflow minus the outflow, which is f of t minus g of t. Its units are going to be the same as the units for f of t and g of t, liters per minute. Maybe you want to give this function a new name. Maybe you want to call it, say, h of t, the next letter. Yeah, this is a function that could be positive or negative. Initially, it's going to be positive here, because certainly because since cosine of 0 is 1 and sine of 0 is 0, initially this is positive and this is 0. Certainly at first, h of t is positive. But it's possible once we get up to pi over 4, the smaller of these t values, it's possible that this could become negative before that point. Positive net flow rate means the inflow is faster than the outflow. Water's flowing in faster than it's flowing out, so the volume is increasing. Water level's going up. Negative net flow means it's going out faster than it's coming in, so the volume's going down. What do you think the integral of the net flow would represent in terms of the water? It's related to volume. Can you add to that? The integral of the net flow is not just the volume. It could be equal to the volume if your volume started out at 0. But in general, it's the change in volume. The integral of a rate of change in general represents the change in that quantity. By the way, before I write that down, I do want to tell you a little funny story. So I made my water blue here, which always reminds me of something from when I was young. I wanted to be an artist when I was young. Actually, I wanted to be a cartoonist. I made hundreds of cartoons. Took drawing classes, took painting class. My art teacher in the painting class in 8th grade, he didn't really seem to like me very much. And he was always criticizing my painting. And I had a painting of a scene with a lake and trees in the background and the blue sky. And he didn't like how dark blue I made my lake. So he came up to me one day and he's like, Kenny, that's what he called me, as Kenny. Kenny, what color is blue? What color is water? And I looked at him, I'm like, I didn't say anything. He's like, come on, Kenny, what color is water? And by now, everybody in the classroom is looking at me. I'm like, Kenny, what color is water? Blue? And he's like, no, water's clear. He didn't say dummy, but it felt like he said dummy. And everybody laughed, okay? Everybody laughed at me. But, okay, of course, water reflects the sky, so it does look blue quite often. But I actually looked it up. It actually does have a measurably slight tint of blue to it, even though it mostly seems clear. So, okay. I'm going to color my water blue. The change in the volume is what the integral represents. Symbolically, people would often write that as delta V, right? Capital Greek letter delta, looks like a triangle, is the common letter used for change in volume in this case, is the integral of the net flow. But before I write down the integral of h of t, or I want to write something else, I'm going to write what I'm going to call a conceptual equation. What's a conceptual equation? It's more of an idea than a literal equality. To find the total change in volume, add up the little changes. Make sense? Where adding is denoted by not a summation sign, but an integral sign. And the little changes are denoted not by delta V's, but dV's. Huh? What in the world is that? It's a conceptual equation. You should realize this is not rigorous math. Not rigorous math. Rigorous math. It's a helpful conceptual equation, or I also use the phrase convenient fiction. I'm pretending the integral sign means add, summation. But I'm not writing a capital sigma, I'm writing an integral sign. What are these dV's? These are tiny changes in volumes. I'm even going to use the word infinitesimal. Infinitesimal changes in volume. Wait, what's an infinitesimal? It's essentially like 1 over infinity. Got infinity, that's an infinite quantity. Take 1 over infinity. Wait, doesn't that equal 0? No. 1 over infinity doesn't equal 0, though many people will write that it equals 0. That's technically not right. It's a convenient fiction sometimes. Does it equal some positive number, some really tiny positive number? I don't know, 10 to the negative million power or something? No. Doesn't really equal a number at all. Though if it did equal a number, it'd be much smaller than 10 to the negative million power. What, 10 to the negative billion, trillion? 10 to the negative Google? 10 to the negative Googleplex? No, even smaller, but still positive somehow. Okay, it doesn't exist there because there is no smallest real number. It doesn't exist in the standard real number system because you can always make positive real numbers smaller by dividing them by 2, for example. So there's no smallest positive real number. This is just a convenient fiction, conceptual idea for the sake of building intuition, not doing rigorous math. When I sat in my science classes and my teachers would write these kinds of things, I'd be like, what in the world are you doing? How do you know you can do that? And they say, because it makes sense. They didn't say dummy either. Okay. They just say, because it makes sense. But they had to default to because it makes sense because they didn't know how to prove it. And they maybe didn't know it was not rigorous. It's okay. It's an idea. I am now about to write an expression that does represent an actual quantity, an actual real number. And that quantity is the definite integral of h of t from a to b. You could say that's a conceptual equation perhaps too, but I mean, the true equality is between these two things. There's a true equality, and the one in the middle is just a convenient fiction. So that's not a rainbow there. That's a long curved equal sign. True equality there. But even this, though it is an actual number, and if h of t is above the graph, it's the area under the curve. It's above the axis. It also can be thought of conceptually in terms of convenient fictions. You can imagine essentially that dv equals h of t dt. What is that? Am I saying dv is h of t times dt? Yes and no. Technically, no. Technically, when you write h of t dt here next to the integral, you are not multiplying h of t and dt. Technically, the dt is just saying, hey, the variable is t, integrate with respect to t. But that's not how Leibniz thought about it when he wrote this. He pretended this was a multiplication. Did he actually think it was a literal multiplication? I'm not sure. It's not a literal multiplication, but we pretend. This is an infinitesimal change in time. Infinitesimal change in time. And h of t is the net flow rate, not an infinitesimal. The units here for time are still in minutes. It's an infinitesimal amount of minutes. The units here for the net flow rate is liters per minute. The units for the quote unquote product, you would cancel the minutes and the units would be liters for the product. Volume. This is very analogous to distance equals rate times time. Volume equals flow rate times time. But we're thinking of it, dt as being this itty bitty tiny amount of time. And during that itty bitty tiny amount of time, the volume changes by an itty bitty tiny amount as well. I'm going to emphasize this kind of perspective a lot in this course. It's not rigorous math, but it's okay. It helps us get right answers. And more importantly, it helps us understand the meaning of integrals and how to apply them. Especially we'll see in chapter 8 a lot, like every section. You might even say it's the most important thing to get out of this class, even though it doesn't necessarily directly apply to doing problems. You want to understand, you want to do more than just solve problems. I mean, that's important, but you want to understand what everything means. In the big scheme of things, that's probably more important than solving problems. I mean, yes, you want to solve problems, you want to get right answers, but you want to understand what it all means. And it's not easy. It takes a while for this to sink in. So if it's not sinking in right now, it's okay. We'll keep working at it. All right, now let's actually do the calculation to find the change in volume over some interval of time. Should I go 0 to pi over 4? I could. Actually, with the previous class, I went 0 to pi over 12, so I'll stay the same with you guys. So I made it a pi over 12. I could do 0 to pi over 4, but that's what I pick is pi over 12. How long is pi over 12? We are in minutes here. Pi over 12 is about 0.26 minutes. How many seconds would that be? About 16 seconds. So this is the change in volume over the first 16 seconds or so. Is going to be the integral of h of t. That'll be the integral from 0 to pi over 12 of the function is 3 cosine 2t minus 4 sine 3t. Let's go ahead and do this just using the fundamental theorem of calculus right away. One of the main things we want to do today is get some practice with substitution, though. So we'll also do at least part of this integral with substitution. But let's just guess, right? Guess an antiderivative of this. Not a wild guess, but an educated guess. Integral of cosine is sine, right? Derivative of cosine is negative sine, but integral of cosine is positive sine. Probably got to have a 2t in there. I'm just doing educated guessing here. How about the 3 there? How do you deal with that? Well, when you differentiate this, I should say, you're going to get an extra factor of 2 being multiplied because of the chain rule. There's a 3 there instead of a 2. How can we compensate? How about make it a 3/2? Right? Check in your mind with me. When you differentiate this, you'll get an extra factor. You'll get a cosine. You'll get an extra factor of 2. 3/2 times 2 is 3. Integral of sine is negative cosine. We already have a minus sign there. 2 minuses are going to make a plus. And because of the 3t in there, we're going to have divide by 3 out here. The minus 4 will become a plus 4/3. So I'm finding this antiderivative by guessing, educated guessing. You should be able to do this on Friday's quiz by educated guessing. Evaluate from 0 to pi over 12. Be careful. First plug in pi over 12. 2 times pi over 12 is pi over 6. Keep plugging in. I'm not done plugging in pi over 12. Pi over 12 times 3 is pi over 4. Now subtract what you get when you plug in 0. Notice the parentheses. I'm subtracting this whole thing. Memorize values of trig functions. Let's see. Sine of pi over 6. Pi over 6 is 30 degrees. Sine of 0 is 0. Sine of 30 degrees is 1/2. In radians, sine of pi over 6 is 1/2. Pi over 4 radians is 45 degrees. You may remember this is square root of 2 over 2. Sine of that is also square root of 2 over 2. Sine of 0 is 0. Cosine of 0 is 1. 3/2 times 1/2 is 3/4. Then I get a plus, let's see. Do a little cancellation here. It looks like 2 root 2 over 3. Then minus 0, minus 4/3, minus 4/3 in the end. Get a common denominator of 12. 3/4 is going to be the same as 9/12. Put a 9 up there. Here I have to multiply the top and the bottom by 4, so I get plus 8 root 2. Here, multiply the top and the bottom by 4, I get a minus 16. Looks like 8 root 2 minus 7 over 12. And I did do this in the previous class. I believe that is correct. Mathematica. In your typesetting palette, click the integral button. Lower limit is 0, tab up. On a pi over 12, I can do escape, T escape, and then divide by 12. Use parentheses here, because we got the difference of two functions. It won't work if you don't use parentheses here. 3 cos 2t minus 4 sine 3t. Notice the capital C and capital S. Notice the square brackets. dt, I made a t there at the end. Yep, that is the same thing. And that turns out to be a fairly small number. Percent sign refers to preceding output. / n does a numerical approximation. About 0.36 liters is the change in volume, not the actual volume. To find the actual volume, you'd have to add on the initial volume. Maybe it's 5 liters. And then the final volume in such a situation would be 5.36 liters. This could have been negative. Net flow rates can be negative. Integrals of net flow rates can be negative. Change in volume in that case, negative means you have less volume at the end. Water level goes down. By the way, instead of doing a tank, I also could have thought about a different application. The flow rates could have been flows of money. Could have been an economics application. Money flowing in and money flowing out. Like literal bills? No, right? It's easier to imagine actually as electronic transfers. And if you've got a company like Amazon, say, they are getting thousands of dollars every second of every day, and they're paying thousands of dollars every second of every day. I don't know how you do accounting in such a situation. How do you know all those transactions are right? I'm sure there's mistakes, right? Yeah. But they can think about flow rates of money, model them with functions, and integrate the net flow rate of money to find the change in money instead of the change in volume. How much does their net balance in all their bank accounts change by? It's the same principle, just different units. Probably you'd call it delta M for change in money instead of delta V for change in volume. H of t would be in, say, thousands of dollars per second, and dt would be an infinitesimal amount in seconds. But if these functions were the same one used, we get the same answer, but this would be in thousands of dollars instead of liters. Okay. Let's also emphasize a property of integrals that you should know before we talk about substitution. The property that I'm thinking of is that the integral of a linear combination of cosine and sine with the coefficients 3 and -4, the integral of such a thing is the corresponding linear combination of the integrals of each individual function by themselves. In other words, I could have done the problem by saying the integral from 0 to pi over 12 of 3 cos 2t minus 4 sine 3t is 3 times the integral of cos 2t minus 4 times the integral of sine 3t. I could have done that, and I could have done each of those integrals individually, multiplied the first one by 3, the second one by 4, and subtracted. I won't take the time to do it, but I could have. I'd apply the fundamental theorem of calculus to each one of these integrals. Now, you might argue in this example that's more work than it's worth, but there are some examples where it might be beneficial to break it up into pieces. That's a special case of a more general property. That the integral, the definite integral of a linear combination is C1 times F1 of X plus C2 times F2 of X, etc., plus through Cn times Fn of X is C1 times the integral of F1 plus C2 times the integral of F2, etc. The last one will be Cn times the integral of Fn. This is a very important property. I forgot my dx there. I should not forget my dx. It's got a name. It's called, well, mathematicians call it linearity of the definite integral operator. Scientists tend to call it, also known as superposition. So when a scientist uses the word superposition, they don't always mean this, but sometimes they mean this. There's a similar property for derivatives. Derivatives are linear too. They satisfy a superposition property too. Before we do substitution examples, let me also emphasize we can think about all this graphically. I could plot, for example, the net flow rate from 0 to pi over 12. It does happen to be the case that this graph just barely goes negative by the time we reach pi over 12. It looks pretty straight. It's not straight. Appearances are deceiving. The integral that we got, the final answer of about 0.36 liters, is indeed the area under the curve when the curve is above the axis, minus the area, this little tiny area above the curve when the curve is below the axis. This area over here is evidently a little bit bigger than 0.36. Maybe it's 0.38 or something. And this one might be 0.02. And so 0.38 minus 0.02 would be 0.36 to get the final answer. I'm just guessing those numbers. I should also mention that you can plot each function 3 cos 2t and 4 sine 3t that you were subtracting here individually. 3 cos 2t is the orangish colored graph up here. 4 sine 3t is this green graph here. Over the interval where the inflow, orange, is greater than the outflow, green, from 0 to about 0.24, the area between the curves is the same as the area under the blue curve. To find the area between two curves, integrate their difference. That's what I'm trying to emphasize here. And it's the same as the area under the blue curve, which is the graph of the difference itself.